Most data points cluster around the center, which is like the average, creating like the highest peak of the curve. As values move farther from the average, they become less common on both sides equally. The shape is symmetrical, and it's also called a normal distribution because it naturally appears in many real-world situations. The center represents mean, median, and mode all at the same point in a perfect curve. So who discovered and developed it? It was developed primarily by Carl Friedrich Gauss, a German mathematician known for major contribution to statistics. Gauss was called the Prince of Mathematicians due to his influence on modern math and science. There's also earlier foundational work which was done by Abraham de Moivre, a French mathematician studying probability theory. De Moivre first noticed patterns in repeated random events like coin flips and gambling outcomes. Gauss later expanded this idea by applying it to real scientific data, and the distribution is also known as the Gaussian distribution. And that's Abraham de Moivre, that's Dr. Gauss. And it originated from early probability studies in the 1700s involving repeated random experiments like coin tosses. Abraham de Moivre observed that large numbers of random outcomes formed a predictable pattern over time. Carl Gauss later studied measurement errors when observing stars and planetary positions in astronomy. He discovered that these errors were not random but followed a consistent symmetrical pattern. When plotted on a graph, these patterns formed the bell-shaped curve we use today, and this showed randomness can still produce highly predictable overall distributions. Some key properties of the bell curve is that about 68% of data is close to the average, and about 95% data is within a wider range, like around the average, and about 99.7% of data falls within an even larger range, meaning almost all data is included. This is called the 68 to 95 to 99.7 rule, and only applies to bell-shaped distributions. Most data is in the middle, and extreme values are rare on both ends. This pattern helps predict how data spread in real-life situations. And it's still important today because it helps interpret large sets of data and allows scientists and researchers to predict probabilities of different outcomes. It helps identify outliers, and it's usually used in widely in fields such as science, economics, psychology, and education. It forms the foundation of many statistical models used in modern data analysis, and it makes it possible to understand patterns in complex systems. Some real world examples are test scores, human heights, IQ scores, and reaction times. And thank
you. Any questions for Ashif?
I have two questions. Is it like an interquartile range for a number line?
Yeah, I think so.
And does it always have to be a bell curve? Or could it be like more widened out or more?
Yeah, it could be more like it's just symmetrical. Overall, yeah, that's.
What would be like your most known example of like what the bell curve is? Like 20 people chose the hot dog burger or something.
It's like usually used for like stuff like this, but it can usually be used for like anything like that.
The shape of the graph itself is bell curve, yes?
Yeah.
Moreover, if we're gonna find the area under this graph, it's gonna be 1, because what we know from the probability course, huh? What did we learn the first 6 weeks of the course? Huh? Yes, Porter.
Probability like always adds up to 1.
all probabilities must add up to 1. So for this curve, specific one, that the area under the curve, regardless how wide is it, area always will be 1. Okay, so it has lots of complications.
Is it always accurate?
What do you mean always accurate? There are many different bell curves, different shapes, can be wide, can be very narrow, yes?
No, I mean like, let's say in this IQ graph, right? Let's say that
Uh-huh.
there's like more people with like 55 IQ than 70.
It depends what is the question asking you, yes?
Or if
You
it's-
might be within the range of certain IQs, yes? But anyways, we are not gonna, usually we do not integrate this graph because the function itself is very difficult. But people generated a table which is called standard normal. So any bell curve I could convert into a special bell curve, which is called normal, standard normal, and mean would be where? Do you remember, Kashif?
The middle.
Middle, where is the middle curve for the standard normal? At the y-axis, the 0, yeah, and the standard deviation will be 1. So that's like instead of all the computations, yeah. Back then, people didn't have calculators, correct? But they did computational part, which tables I show you that any bell curve can be sort of converted through the formula to the standard normal. So standard normal.
Because you
Go ahead.
the price of stocks, right? Daily changes, right? Over like 30 years, long time, so you have maybe like 10,000 observations, right? And you plot it, right? It could look symmetric, right? There's a lot of evidence that the way that plot dies as you go to the left and right is much slower than the normal distribution, actually. So big moves are more likely than would be enormous. This is a very well-known phenomenon in stock returns, you know. So people say, oh, it looks like a bell. It does look like a bell. But the question is, how quickly does the probability die as you go to the two ends? And the histogram, which is based on, you know, actual data, it dies slower, quite a bit slower.
Yes, and Porter was presenting the law of large numbers also, yes, so that it actually approximates larger sample size,
Yeah.
closer to mean it goes, yeah.
Is he saying like at one point stocks will have like a high point and it's gonna be like this?
No, what I mean, in other words, let's say, stock prices, every single day, look at how much they change. So one day they go up 2%, right? So do this for like 20 years. So you have like, you know, I don't know, 2,000 data points, right? Just plot them, you know, with the histogram, you know, how many numbers are in a given range, right? It looks somewhat like that. But if you examine it more carefully, and look at how the likelihood dies as you go to the right or to the left, it will die slower than the exponential that characterized the normal distribution.
Oh, yeah.
It will die slower. It's known to be, it's another distribution that seems to match it better. It's called Student's T. So people wonder, what is it, is there a message in that? Like, you know, this has been studied a lot. It's very easy to do, right? You know, just plot 2,000 points and see how quickly it dies. And dies, you know, but not that fast. This is very fast. As he said, right? 99.7%, you said?
Yeah.
Right. That one of the actual data doesn't die as fast.
So then you
Yeah.
Yeah, if you're
Sorry,
interested
yeah.
in this, you should visit Museum of Math, MoMath, at the new location, probably they installed it too. There's a board called Galton board that is actually showcasing. So imagine like some sticks coming out of the board in the shape of a triangle, and then balls are coming from top.
Yeah, yeah.
And whenever ball hits a stick, it has a 50% chance to go to left or to right. If you just sit in front of the board and watch it like long enough, you see that the balls eventually get the shape of the bell curve actually. So it's a natural phenomenon that happens.
Cool, any other questions? All good? Thank you, Kashif, yes.